this class I introduced the concept of mass balance in a unit operation. Mass balance represents the quantity of liquids that are flowing in with respect to the quantity of liquids that are flowing out. So if there is no reaction or if there is no evaporation or loss of liquid, whatever comes in should be equal to whatever goes out. That means number of streams of liquid that are coming in should match with the number of streams of quantity of the number of streams of liquid that are going out. So it is very useful to see or to calculate what is the volumetric flow of liquid that is flowing out. So for example, this could be a distillation column. You may be having 2 feeds coming in at certain flow rate and you may be having 2 feeds going out at certain flow rate, and then you can calculate what will be the flow rates of the liquids that are going out. That is one. The second point is you can also do a mass balance for a particular species. Imagine there is acetic acid in that stream, you can do a mass balance for acetic acid that is entering the stream is equal to the acetic acid that is leaving the entire unit, assuming that acetic acid is not getting converted to any product. So the amount of acetic acid entering should match exactly with the amount of acetic acid that is going out. It can be in 2 streams and it can be going out in 2 streams, but still the total amount should match, assuming that there is no loss or no degradation. And this is done at a steady state, because if you are starting your unit operation when it is in unsteady state condition, there will be accumulation inside the unit. So these numbers will not exactly match, but once it has reached a steady state, these should match exactly. Just like mass balance, you also have something called heat balance. That means the amount of heat you input, the amount of heat that is going out, and the amount of heat generated inside the unit, and the amount of heat that is lost to the surroundings, they all should be related to each other. For example, if you look at this particular flow sheet, you are having 2 fluids coming in and each fluid has certain amount of heat, and there are 2 fluids going out and each fluid has certain amount of heat in them. You are also generating heat. This heat could be generated because of a reaction, or it could be because of viscous forces, and you are also losing heat. The heat lost could be because you are cooling the contents, or it is lost to the surroundings because the unit may be losing heat to the surroundings. So all these heats should balance with each other. That means total amount of input heat should balance exactly with the total amount of output heat. Now let us look at what is the heat content of a fluid that is coming in. This will be equal to the mass of that fluid that is coming in, the specific heat of the fluid multiplied by the temperature corrected at certain datum condition. Okay. So mCp delta T is equal to the total heat. This we have read long time back. Similarly, for this particular fluid it will be the mass, that means flow rate into density into specific heat into delta T, that is the temperature at which it is corrected to at certain value. Similarly, the heat loss will also be the mass, that is flow rate into density into specific heat into delta T, and similarly for the 4th stream the total mass is flow rate into density, specific heat into some temperature. Heat generated could be because of exothermic reactions taking place inside. So you will be knowing what is the heat generated inside the reactor, and similarly heat loss may be because you are cooling the contents or there is a loss to the surroundings. So once you know that, you can balance all of them together. So the heat inputs, as I said, is a sensible heat due to inlet fluid, heat added by heating medium or exothermic heat, and then heat removed is heat removed by the coolant, heat lost to the surroundings, or heat removed due to the outflow of the fluid. Okay. The outflow of the fluid is like this, these two. Okay. So when you do a heat balance, what do? You say all the input heats that is on the left hand side of this equation should match with all the output heats that is on the right hand side. that is the heat input, heat generated, which is equal to heat output, heat loss. So how do you calculate the heat? Volumetric flow rate into density. Volumetric flow rate into density gives you the mass flow rate into specific heat into delta T. How do you calculate delta T? That is the temperature of the fluid minus certain baseline temperature, that is the delta T. So that is how you do a mass balance, I am sorry, that is how you do the heat balance. Heat balance is very important to find out how much heat I need to put in to heat a contents. For example, if I am trying to increase the efficiency, I would like to heat. If it is an exothermic reaction, you would like to cool, so I would like to know how much coolant I need to pass. So for all these calculations I need to do something called the heat balance. So in each of the units we design in a downstream, we need to carry out both mass balance and heat balance to see, am I having any losses in the mass, or am I having any losses in the heat, or the amount of heat required to raise the temperature of the contents of the fluid. Now let us look at few flow sheets let us look at some few flow sheets related to downstream, and I will try to focus on the important salient points, what type of downstream units are used, and what are the costs involved in each one of these downstream. So let us take a few examples. It just gives you an overview of how a typical flow sheet will look at. I just introduced about fermentation of sugar for production of alcohol. Let us look at the same thing again. Generally yeast is used in the industrial scale for producing ethanol. Okay, so you have sugars. If you take countries like Brazil or India, they use cane sugar for production of alcohol. If you take USA, normally corn is used for production of alcohol. There are different types of yeast species which are used for the fermentation. Saccharomyces, this is generally used normally in industrial scale. The raw material cost takes care of almost 70% of the cost of ethanol production. So if you can reduce the raw material cost, you will be able to reduce the production of ethanol. The main problem with these organisms are they are not very tolerant to ethanol. That means they are tolerant to only maximum. There are certain genetically modified yeast species which can take up to 15% ethanol, but generally 8, 9, 10% of ethanol the fermentation is stopped because the organisms are not tolerant. So you see that the broth after fermentation is extremely dilute. If it is 10%, 90% contains water and other biomass, dead cell debris and salts. So you need to recover the ethanol of only 10% from this large amount. So that is the main reason, it produces a very dilute concentration of ethanol. The optimal temperature for thermophilic organism is about 50 to 60 degrees centigrade. So because these organisms have genetically modified, they are able to be more tolerant towards ethanol, number one. Number two, they also can be operated at slightly higher temperature. As you can see, almost 60 degrees C we can operate, and the fermentation is generally done in batch mode, and it takes about 40 hours for the entire fermentation process. Okay. Once you have done the fermentation and you are talking about 10% ethanol, you need to purify it to almost 90-95%. So obviously you need to do lot of distillation, that is where distillation is there, and initially you have a very large distillation column which will increase the ethanol amount from 10% to almost 30-40%, and then finally to a large number of distillation column which raises it up to 90%. One important point, if you all remember, ethanol water forms an azeotropic mixture. That means you cannot purify the ethanol beyond 89% unless you have certain azeotropic separation techniques if you want to reach up to 99 or almost 100% ethanol. So azeotropic distillations involve adding a third component, adding an entrainer so that the azeotrope is broken, or sometimes you add an adsorbent so that the azeotrope is broken. So if you want 100% ethanol, you need to resort to breaking of this azeotrope, that is on the right hand side here actually. Now if you look on this side, you have the biomass, so you need to filter the biomass, and then you can dry the biomass, and it still contains certain proteins which can be used as animal feed here. So, this once you dry the biomass, it can be sent for animal feed here. So, this is a typical downstream for the manufacture of ethanol from sugars. So, most of the downstream units, as you can see, is distillation columns and filtration units, and because ethanol is tolerant to high temperature, we can resort to distillation columns. But if you are going for protein, or if you are looking at biomolecules, they may not be tolerant for such high temperature. So, some of the companies involved in the manufacture of ethanol, this is the 2007 data. So, you may have more companies coming into it, just gives you an idea of what type of companies are involved. As you can see, Archer Daniels, they produce 1070 million gallons per year of ethanol. Whereas Sun Energy Systems, they are producing 120 million gallons. New Energy Corporation about 100 million gallons. Another Hawkeye Renewables, they are producing about 100 million gallons per year. So, you are talking about in terms of hundreds of millions of gallons of ethanol per year. Ethanol is not only used into for making alcohol, industrial applications, as well as for consumption purposes actually. Let us look at next product, it is the amino acids. Amino acid is a huge business, multi-billion-dollar business, because they are used in animal feed, they are used in flavor enhancing, they are used in medical products, they are used as a food additive, they are used for even improving the energy processes. So, if you look at lysine, methionine, threonine, they are used in animal feed. Flavor enhancer, monosodium glutamic system acids, I think we are all used to this monosodium glutamate used in Chinese food and flavoring. Serine, aspartic acid, they are all flavor enhancer. If you look at glutamic acid, lysine, methionine, we are talking in terms of about 0.5 to 1 million tons per annum production. This is the 2000 data. So, you may be adding about 10-15% to much more than that actually. So, the first two are made from fermentation, and this is made by chemical synthesis actually, okay. And L-aspartic acid, L-alanine are made through enzymatic synthesis. So, when you talk about, when you say enzymatic, you are talking about a biotransformation. So, these two are made by fermentation, and this is made through chemical route, and these are made through biotransformation. So, the major producers of amino acids, Japan, US, South Korea, China and Europe. So, they are talking about an increase of about 2.5% annual growth. Monosodium glutamate, we are all used to it, it is a flavoring material, it was introduced in the year 1909, and the business is about $1 billion US, that is a big business which is used in flavoring Chinese food. L-aspartic acid, L-phenylalanine, L-lysine hydrochloride, L-leucine, they are all produced in batch products actually. All these also are used in dietary supplements, they are used as artificial sweeteners. So, the first two are used as artificial sweetener aspartame, again that is a very big business, with more people having diabetic and glucose intolerance, this artificial sweetener business is also becoming big. Raw materials contribute the largest in the production cost, and remaining is waste treatment and utilities. So, 67% of the cost is due to the nutrient media, 12% is because of ammonium hydroxide used in ion exchange column, 13% is the cost of pre-coating. Why do you pre-coat? You want to pre-coat all these amino acids because you want to prolong its life, you want to prolong its shelf life, you want to prevent degradation, that is why you need to pre-coat these amino acids, and about 13% of the cost is because of the coating of this amino acid product. If you look at the hardware side, we looked at the chemical cost. Now, let us look at the hardware side. Reactors contribute 33% of the total cost, and then if you look at the downstream side, remaining 67%. Crystallizers, 28% of the hardware cost is because of crystallizers, 19% is because of storage tank, and 12% because of the filters. So you see, once you know the contribution of cost by each of the hardware unit in the downstream, if you can reduce the size of the unit, obviously you are able to reduce the cost of the entire plant. In L-aspartic acid as well as L-phenylanilin production, 95% of the raw material cost is due to the media. So if you can optimize the media efficiently, you can reduce the operating cost in the manufacture of L-aspartic acid and L-phenylanilin. Once again, reactors, crystallizers, storage tanks and filters contribute the maximum in the overall hardware cost. Let us look at the downstream. The amino acid after its production is recovered from the broth using several downstream steps. You also use something called reverse osmosis, and you also use something called chromatography. We are going to talk about each one of these downstream units in more detail in the forthcoming classes actually. Industries which produce these amino acids, companies in France, companies in Germany, companies in China, some of them using a protein extraction method, some of them using enzymatic resolution, some of them using biocatalysis and fermentation product. So this is a picture which tells you the raw material cost breakdown for the manufacture of L-leucine and L-lysine. So 67% of the cost is because of the nutrient media. So you can focus on optimizing the nutrient media. A typical nutrient media will contain a carbon source, a nitrogen source, micronutrients, salts, metals and so on. So if you can reduce the usage of them, obviously you can impact this cost. Next comes the use of ion exchange ammonium hydroxide. So if you can reduce the usage of ammonium hydroxide, obviously you can impact here. Next is again hydrochloric acid, which we use in the ion exchange for regenerating the ion exchange. So if we can reduce the usage of HCl, you can impact on this particular cost. Then finally a large amount of cost is incurred in the pre-coat. So if you can optimize on the pre-coating of this amino acid, you can impact on this particular area. The total equipment cost in the manufacture of L-leucine and L-lysine, 3% is because of the reactors. So if you can bring down the reactor size, you can reduce the number of reactors, obviously you can impact here. And then again 28% is the crystallizers, 19% is the storage, 12% is the filters and 7% is the ion exchange. So one can look at how to reduce the size of the filters, how to reduce the size of the storage tank, and how to reduce the size of the crystallizers. If you look at the aspartic acid and L-phenylanilin, large amount of cost is because of the nutrient media. So one needs to focus, one needs to do more R&D in trying to optimize the nutrient media. You can see 95% of the cost. So there is a lot of scope to reduce the cost of the raw materials in the manufacture of L-aspartic acid and L-phenylanilin, if you can try to focus on the various components of the nutrient and try to reduce the amount of nutrients used here. And 2% of the cost is because of the ammonium hydroxide usage in the ion exchange resin actually. Again if you look at aspartic acid, L-phenylanilin, reactors take up 31% of the cost, crystallizers take up 29% of the cost, storage tank takes up 19% of the cost, and filter takes up 12% of the cost. So reducing the size of the filter, reducing the size of the storage tank, reducing the size of the crystallizer, one can really bring down the total equipment cost in the manufacture of aspartic acid and phenylalanine. Now let us look at the next product, acetic acid. Acetic acid is used in the production of polyethylene terephthalate, PET. Okay, that is a polymer. PET is a polymer used widely. Almost all the soft drink bottles are manufactured using this polymer. Cellulose acetate, which is used in the photographic film, polyvinyl acetate, which is used in the glue, and many synthetic fibers, they all have this particular polymer present in it, and this polymer is made from acetic acid. So acetic acid has very large usage in a large number of polymeric products actually. So acetic acid can be manufactured both by synthetic route as well as the bacterial fermentation. For example, vinegar, that is another name which we use quite frequently and quite a lot in food, is also made, but it is made using a biological route. Vinegar, about 10% of the world production is vinegar, and that is made using the biological route actually. So most of the world food purity laws require that vinegar that is made for food application must be based on the biological route. So that means if you are wanting to make a PET, the acetic acid can be made through chemical route, but if you are interested in manufacturing vinegar, then the acetic acid has to be manufactured using biological methods. So most of the acetic acid in the chemical route is based on the methanol carbonylation. So it is a homogeneous process using methanol as the raw material, and it is a carbonylation reaction. So the carbon monoxide is put inside methanol to make the acetic acid. If you look at the biochemical route for manufacture of vinegar, you use a bacteria genus called Acetobacter. Even certain genus of Clostridium can also be used for making acetic acid. The advantage here is it does not have to go through ethanol, because once you want to go through ethanol is very toxic for many organisms, and many organisms are not able to survive in the ethanol medium. So Clostridium is another organism which can convert the sugars into acetic acid without going through ethanol in between. So what are the downstreams? So once you make the acetic acid, you have to filter the media, so for removing the particles, biomass and solids, and then you resort to electrodialysis to remove and neutralize the salts that are present, because you are going to have a lot of salts present, so that the acetate becomes acetic acid, and then finally you resort to distillation to recover the acid. So these are the three downstream steps in acetic acid manufacture. Initially the filtration to remove all the biomass, cell debris, solids, and then using an electrodialysis you convert the acetate into acetic acid, and then finally you have the distillation. So many different ways of filtration can be resorted to, so many different ways of electrodialysis can be resorted to, and so many different ways of distillation also can be followed actually. So if you want to separate the acetic acid from water, you can use fractional distillation, you can use azeotropic distillation, you can use extractive distillation. So these are three different types of distillation, or you can use a solvent so that the acetic acid alone is extracted from the dilute media. You can also resort to adsorption, so carbon can be used for adsorbing the acetic acid. So all these different techniques can be used, and each one has got advantages, disadvantages. There is also a cost factor involved. Some of them are expensive at certain scales, some of them are cheaper at certain other scales, and so on actually. So one needs to decide depending upon the cost factors. Okay. So this is a typical flow sheet for the manufacture of acetic acid. So the fermentation takes place here, and then you have the downstream. So you have a filter, solvent extraction, so many solvent extractions, and then the distillation, then the solvent is coming here which can be sent back into the solvent extraction unit. So the distillation will produce acetic acid. So this is a typical acetic acid manufacturing plant. This is how it looks like actually. Let us look at the next product. It is a 2,3-butane diol. 2,3-butane diol is a valuable fuel additive, and it compares very well with other liquid fuels. It is also used in printing inks, perfumes. It is also used as a fumigant, moisturizing and softening agents. It is also used as a plasticizer in explosives also. So and it has got some applications in pharmaceuticals as well as a carrier, drug carrier molecule. So it is widely used in a wide range of products, and it is produced using these two microorganisms. Generally the second organism is preferred because it can utilize a large number of sugars for converting into 2,3-butanediol. So, hexoses can be used, pentoses can be used, or even disaccharides can be used, which can be fermented to 2,3-butanediol. The fermentation also produces little bit of ethanol, that is one point. So, ethanol tolerancy is very important, number 1. Number 2, butanediol itself is toxic to these organisms. So, what you have to do is, as soon as you produce butanediol, you have to remove the butanediol and then send the broth back into the reactor for further fermentation. So, extraction is part of the fermentation here. Several solvents are used for extracting butanediol. It includes say N-decanol, dimethyl phthalate, propylene glycol, oleal alcohol. So, you can use different solvents. Each solvent has different affinity to butanediol or partition coefficients to butanediol, and the yield of butanediol into these solvents depend upon the operating conditions also. So, butanediol has a very high boiling point. So, you cannot use a distillation column and hope to get butanediol at the top of the distillation assembly. So, that is the main problem. So, extraction is the only way of extracting butanediol after the fermentation. So, how do you do it? First, the medium is passed through a filtration membrane. So, once it passes through, the cell free medium is obtained, and then you use a solvent for extraction, like for example N-decanol. You can use a 4-stage countercurrent extraction. So, what does countercurrent means? The broth which is free of cells pass in one direction, and the extracting solvent like N-decanol passes through another direction. That is what is called countercurrent. So, butanediol is extracted using a 4-stage countercurrent. You can also use a car extraction column for extracting butanediol. Here oleal alcohol is used as a solvent. You can also use a solid supported liquid membrane for extracting, and then later on you can remove the liquid membrane so that the butanediol is extracted. So, this is a very good process. You can extract almost 94% of the butanediol. You can also use a salting out technique by adding potassium carbonate. So, I add potassium carbonate, so because of the changes in the solubility, butanediol precipitates out. So, that is another technique. So, you see so many different approaches can be used. We can use extraction, countercurrent extraction using a solvent and decanol, or we can use a oleal alcohol with a car extraction column. We can use a liquid membrane, or we can use a salting out technique by using potassium carbonate as the salting out material. So, each one can be used, and each one gives you a different amounts of extraction efficiencies. So, a typical schematic for the butanediol process: you have the fermenter on the left hand side, okay. Then immediately after the fermentation you have a microfiltration to remove the cell and biomass, which can be put back into the reactor because they are active biomass. So, it can be put back, and then once you get the cell free liquid, you can resort to extraction, and the solvent can be removed from butanediol using a distillation column, and the solvent can be put back into the solvent extraction unit. So, you can have a closed system like that. So, solvent is put inside in a countercurrent manner, and the solvent and the butanediol can be put inside a distillation column. Solvent can be extracted, distilled from the top of the distillation column and again put back into the extraction unit. Butanediol can be collected here. There is going to be waste also, whatever solids or unwanted metabolites, that constitutes the waste. So, this is based on a solvent extraction system, but if you are interested to salt out, then obviously what do? You need to add potassium carbonate so that butanediol comes out. So, here in this approach what do? You have a filtration so that the solids are removed, then you have flocculation which will remove floating solids, then you add a potassium carbonate. Because of the difference in the solubility, butanediol settles out, and then we can take out my product here. So, two different approaches, one is based on extraction, another is based on salting out, which I showed you. So, each of these approaches require different types of downstream steps. So, companies which manufacture butanediol, you can see some American companies, some German companies, some Swiss companies, even Chinese companies are there, they all are involved in the manufacture of butanediol. Let us go to antibiotics, streptomycin. This is a first class of antibiotics, that means it came almost 20 years back. These are based on, they are called aminoglycosides, they are the first remedy for tuberculosis also. It is produced by an organism, Streptomyces rhizosus. This drug stops bacterial growth by damaging the cell membranes, hence the protein synthesis. It binds to the 16S RNA of the bacterial ribosome, and hence it prevents the growth of the protein. So, this is the mode of action of this particular antibiotic streptomycin, and hence it was used quite a lot in tuberculosis. Even now it is being used for treating tuberculosis. So, it still got quite a lot of application. It is an antibiotic. Many companies, many drug companies manufacture streptomycin. Merck & Co, Ranbaxy Labs in India, Pfizer, GSK, GlaxoSmithKline, Novartis. So, you can see large number of pharma companies are manufacturing streptomycin because it is still used as antibacterial agent, it is still used in the treatment of tuberculosis. Okay, so, what are the downstream steps that are commercially practiced? First is the clarification of the culture filtrate. So, clarification means you are removing the flocculants. So, it is based on a pH adjustment, and it uses carbon to absorb the unwanted metabolites and waste. Then you are resorting to extraction at a pH of 7, then you are washing the carbon with water, neutral ethanol, neutral methanol. So, you keep on washing until whatever streptomycin has been absorbed on the carbon is collected. So, that is why you resort to multiple extractions. Once you do that, you are precipitating the crude streptomycin chloride with ether. If it contains water, it is going to be a sticky gum. So, you need to remove as much water as possible using ether, and finally you are purifying the streptomycin with ether. Okay. So, these are the various downstream steps. First you are clarifying means you are removing the floating solids, and then you are extracting, and then washing the carbon several times with water, with ethanol, with methanol several, and then you are adding hydrogen chloride and then precipitating it out, and then finally you are purifying using ether from the methanol. So, this leads to a pure product of streptomycin. Product purity is very important in this particular case, because you are talking about a drug, and anything that needs to be consumed by human, it has to pass through the FDA, that is the Food and Drug Authority USA, which stipulates certain conditions for purity. Now, let us look at another product, biodiesel. Biodiesel is a big thing nowadays. It is a fuel for diesel engines. It can be produced from vegetable oil. So, it is a green alternate to the oil which we get from the earth. So, it is a sustainable product, it is a resource which is not going to be consumed. So, there is a lot of interest on biodiesel, and there are different types of vegetable oils which are being looked at for manufacture of biodiesel. Even India is doing some research on Jatropha for manufacture of biodiesel. So, many countries all over the world are looking at vegetable oil based diesel, which can be used in cars or trucks, even in aeroplanes as well actually. So, how is it made? It is made chemically by reacting vegetable oil with an alcohol such as methanol. So, basically it is a transesterification reaction. So, the methanol is reacting with the vegetable oil, that means triglyceride, and producing your product. So, it requires a catalyst usually a very strong base, you use a sodium or potassium hydroxide. Okay. So, you are producing a methyl ester of the vegetable oil. By producing a methyl ester, you are reducing the viscosity of the vegetable oil, and you are improving its properties, the physico-chemical properties, and hence it can be used as a mixture with normal petrol or diesel. That is why it is called biodiesel, because it is made from vegetable oil. So, this is a transesterification reaction. So, the methanol reacts with the triglyceride and then it produces a methyl ester, that is why it is called a transesterification reaction. Okay. So, the reactor will contain an alcohol, that is the methanol, a catalyst and the vegetable oil. Generally the reaction takes place within 1 hour and you use about 60 to 70 degrees temperature. This is a typical flow sheet of a biodiesel manufacturing. So, this is called the reactor. This is a chemical reactor, there is no biological products coming into, you are just adding an oil, you are adding catalyst which is a sodium or a potassium hydroxide, then you are adding a methanol. So, it is not a fermenter or a biocatalytic reactor, it is a typical chemical reactor. Why am I giving this example? Because there is a bio involved in the diesel manufacture, it is a biodiesel, that is why I am giving this example. So, once you produce the biodiesel inside the reactor, there is a separator, because you are having water, you are having glycerol, you are having oil, you are having the biodiesel which is the methyl ester of the triglyceride, and then you are having some catalyst. So, so many things are there present inside. So, obviously you need to separate them, and then you have several distillation columns. By using these distillation columns you are separating methanol, you are separating glycerol, and then you are separating your biodiesel, and then finally the biodiesel is dried here. Dried means the water in the biodiesel is completely removed. So, this is how the reaction takes place. So, you have a transesterification reaction, and then you have separators to remove solids, you have separators to remove water, you have separators to remove the glycerol, then you have separators to remove the oil, and then finally the biodiesel is dried here, which is used as a product which can be mixed up with normal diesel. Glycerol is one of a large side products that is produced during the biodiesel manufacture, and people do not know what to do with this glycerol. So, there are a lot of research being currently done on using glycerol to convert into a value added product, because once everybody starts making biodiesel, there is going to be so much of glycerol that is going to be produced, and very cheap glycerol, and hence the raw material cost will be low. If we can convert it into some value added products, there is a lot of scope. Now, next product we are going to talk about is human insulin. It contains several steps, because it is a product which is going to be used as a drug, as a pharmaceutical product. The safety regulations are very stringent, purity is also very stringent. It is produced intracellularly by the cells. So, the cells have to be harvested, cells have to be broken down, so that the product that is entrapped inside the cells get liberated. So, there is something called the cell harvesting, and there is something called the cell disruption. Okay. So, once you get the intracellular product, that is not the insulin, you need to convert it into insulin, which is done through an enzymatic reaction. So, you need to unfold the protein and then again refold the protein, so that it achieves the desired performance. Now, then it becomes the actual insulin. So, there are certain enzymatic reactions that it takes place, which unfolds as well as refolds the protein, so that the desired activity is obtained. 50% of the manufacturing cost is because of the raw materials, 70% is because of the equipment, and 13% because of the consumables, and 62% of the cost of the hardware is because of the fermentation and the reactors as well, and 29% is due to downstream. So, you see about almost 30% of the equipments that are needed in the manufacture of human insulin is downstream units. So, if I can reduce the number of units, I am going to save on the equipment cost. So, this is a typical flow sheet of a human insulin starting from proinsulin. So, what you do, you have a fermentation, you collect the biomass which is called cell harvesting, and then you break the cells. How do we break the cells? We will talk about it in the future lectures. So, we break the cells so that the intracellular product comes out, and then you perform certain enzymatic reactions which refolds your protein and make it very active, and then finally you purify your product. This is what is called the purification step. So, all these are the downstream steps here once you start collecting your cells. So, if you look at the breakdown of manufacturing cost for human insulin, 50% is the raw material cost, 17% is because of the equipment, 13% is because of the consumables which are using in the various downstream steps. What are consumables? Consumables may be solvents, consumables may be gases which you are using, consumables may be salts which are used for salting out. So, all these are called consumables, and 11% is because of the water which you are using, water disposal. So, that means effluent related cost. So, 50% of the cost is raw material related cost. So, there is a lot of scope for performing optimization so that the raw material cost can be brought down. If you look at the various operations, almost 50% related to reactions, about 30% is because of purifications. As I originally said, this is a pharmaceutical product, so there are a lot of stringent regulations for its purity and presence of non-toxic chemicals. So, you need to spend a lot of effort in purifying this product. That is why 30% of the cost is because of the purification step, 8% is because of fermentation, 9% is because of the primary recovery. So, the reactions which involve the unfolding, refolding using enzymatic bioreactors contribute to 54% of the total production cost of this. So, now I gave you examples of several different products. We started from alcohol synthesis, then we looked at acetic acid, then we looked at several amino acids, then we looked at streptomycin, then we looked at biodiesel, and then finally we looked at human insulin. So, each one has different types of downstream processes depending upon the product stability, depending upon the requirements of the product. You have to resort to different purification steps, and I also showed what is the contribution of each one of these downstream in the overall manufacturing cost. So, once you understand the various contributions of various units in the total manufacturing cost, one can spend more effort, more research and development effort, so that one can reduce the cost involved. So, it is very important to understand the effect of each of these downstream in the total manufacturing of the product as well as the selling price of the product. Most of the biological products are proteins. So, when we are handling proteins, we have to remember several points related to proteins. Unlike a normal chemical like an acetic acid or butanol or butane diol or biodiesel, proteins are biological molecules they lose their stability very fast depending upon the way we handle the pH conditions, the temperature conditions, the presence of toxic materials. So, we need to consider and keep several points in mind, and that is what I am going to list out in the next 3 slides. So, if one is interested in purification of a protein, you need to understand, decide, know the reasons for undertaking this protein purification. That means aims of the protein purification. Am I going to purify this protein for manufacturing, or am I going to use it for analytical purposes, or am I going to use it for characterization purposes. So, depending upon the purpose for which I am doing this purification, the approach or the methodology or the assay I am going to follow is going to be very different. So, you need to understand what are the aims of this purification, what are the chemical physical properties of the protein. You need to collect it from literature. What is the size of the protein, what is the molecular weight of the protein, how many strands it has, what is the percentage of the beta sheets, and so on actually. So, you need to understand the chemical physical properties of this protein. What are the assays for measuring the activity of the protein? So, I need to know those assays. Many a times it may be available in literature, then I just need to bring it to my lab, do some modifications or optimize it so that it suits my conditions. In some cases the assays might not be available, that means I need to develop my own assay to identify the activity of the protein in my lab. So, that may involve considerable amount of time. Now, next step is source of the protein. Where am I going to get this protein from? Is it from a tissue, is it from an organism, which part, what will be the concentration of the protein when I try to extract it from the source? Will it be stable at those particular concentrated condition? So, I need to understand that. Fifth point, I should develop a good extraction procedure for this protein. Am I going to follow a solvent extraction, or am I going to use a salting out type of approach, or am I going to use a page type of approach? So, I need to understand or decide on what will be my extraction procedure. Next is denaturation of the protein. As I said, proteins get denatured very fast depending upon the pH, the osmolarity, temperature, presence of other inhibitors, presence of toxic chemicals. So, do I have to protect my protein during the extraction procedure so that it does not get denatured? So, I need to keep those aspects into. I need to standardize the capture procedure, I need to standardize the intermediate purification procedure, and final the polishing and stabilizing procedure. So, I need to standardize all these things in my lab. Next is storage of the protein. What are optimum conditions for storing my protein? Because some protein may be very unstable at low concentration, some needs very high concentration, some does not require, should not have any water present in them. So, all these aspects need to be considered actually. So, I may be like putting my protein 50% glycerol, or some protein maybe I would like to keep it in serum albumin. Sometimes you have to keep your proteins at minus 70 or 80 degrees centigrade. Sometimes you would like to store your protein in small quantities rather than storing the whole protein in a big bulk. That means instead of storing my protein in a 100 milliliter flask, I may like to store my protein in 500 microliter flasks. So, you need to consider the quantity in which you would like to store. Minimize sample handling at each stage. So, when I am doing intermediate purifications, intermediate assaying, I would like to keep the handling very small, because as I keep handling the protein more and more many times, we are going to have the denaturation of the protein taking place. We have to minimize or avoid use of additives, because additives may be toxic to the protein. It may change the conformation of the protein, the properties of the protein itself may change when I add the additives. Protein may get denatured over a period of time. So, I should minimize or completely avoid the use of additives, and if I have to add additives, I should know whether the additive is going to affect the protein activity over a period of time. And later on, if I have contaminants present in my protein mixture, it is better to remove the contaminants as early as possible rather than keeping the contaminants during the intermediate stages, because if when I am purifying my protein, the contaminants itself may get purified or concentrated, then they may start acting on the protein and they may denature the protein. So, you need to remove the contaminants as early as possible, and one needs to look at it how early we can remove the contaminants, so that they do not get accumulated over a period of time. So, these important 11 steps need to be resorted to if one is handling a protein type of biomolecule, unlike handling a simple chemicals like acetic acid or biodiesel, as I said earlier actually.